Let's go to problem number 3. Second order linear differential equation. There, I wrote 2 proof problems about Laplace transform. And of course, you gotta know the definition of Laplace transform for that. And what is the definition of Laplace transform? Let's see, let's put f of t here. And it is defined like this. Integral going from 0 to infinity e to the negative s times t power times f of t dt. That is the definition. And resulting expression will be a function of s, by the way. And if you really want to make sure, then you can insert t is going to 0 and t is going to infinity. You can explicitly write t's in there if you want to, that is. Okay, using this, you'll have to prove this and then that. Okay, let's do problem A first, and all you have to do, as a matter of fact, is to apply the integration by parts. Okay, here we go, and let me see, shall I expand the font? It's already there. Let me just expand font for the integral part. Okay, all right. Integral from 0 to infinity, e to the negative st, and then we want the function y prime there, so yes, we go y prime here in place of this function f there, because inside we have y prime. And then we just apply integration by parts. This is dv, so we want v, so yt. And then this is u, so we want du. So let's take the derivative. What do you get? Exponential stay the same. And by chain rule, we have negative s. So the first line comes from the integrating power. Okay, next, this negative simplifies into positive, and then s is just a constant as far as t is concerned, so I can bring it out. Perhaps I should do that to make this a little bit more explicit. Yeah, t is the variable, so s can come out. And then if you look at this integral here, what is this? This is precisely the same as the definition of Laplace transform. So this is capital Y of s. How about this part over here, u times v part? Well, plug in infinity, plug in 0, plug in infinity e to the negative infinity times y, that's assumed to be 0. And you see, if that doesn't go down to 0, because y is growing not quickly enough, in that case, Laplace transform is undefined, and we don't deal with those kind of situation in this course, or ever. So e to the negative infinity times a function, that's always 0. And then t is equal to 0, then e to the 0 power. And e to the 0 power is, of course, 1. So we have simplification like this, s y of s minus y of 0. Next, let's consider the same kind of formula for second derivative. One way to do this is to apply the integration by parts twice. If you take the integration by parts, you're going to get some expression of Laplace transform y prime and do it again to get the original, but you don't really have to, as a matter of fact. Turns out you can use this. How? All right, here we go. Y double prime is basically derivative of y prime. So if you put it over here in this formula, and that's s times Laplace transform of the original, which is this. And then y of 0, the original, but original is the first derivative because we started from the second derivative. So we get the first line. And then, of course, you can make this observation. Over there, I can go back to the previous formula again and then use it. And then sy minus y of 0. Some further algebra yields what we want, s squared capital Y minus sy of 0 minus y prime of 0. The last method, without the integration parts, readily extends over to arbitrary derivatives through mathematical induction, but I'll leave the detail to you guys. Okay, now that we have this formula and that formula, let us apply those two formulas to solve this second-order linear equation, non-homogeneous second-order linear equation. All right, if you don't use Laplace transform and use some other method, like method of characteristic equation and undetermined coefficient, and do it, that's fine. It'll turn out it's gonna be really time-consuming to do so because we have two non-homogeneous functions here, so we have really a bunch of characters to identify, so we're gonna get really messy system of linear equation. Theoretically it'll work, but it's gonna be a pain in the rear end to work it out. If you use Laplace transform and some help of computer algebra system, or you can do just direct computation too, and you can handle it. And as a matter of fact, okay, here we go. Taking Laplace transformation of both, we get left-hand side, right-hand side like this, and then we can separate all those addition and coefficients. Use the linearity and we get that. Next, let's use Laplace transform formula for second derivative and the first derivative and the original, and the right-hand side exponential and then e to the negative power, and should be in your formula sheet. Okay, all right, and then our bread and butter. Let's see. Plug in initial value condition, and then what do you get? Y prime of 0 is 0, so this one drops out. And then y of 0 is -1, so this instead of negative we have plus, and we have sign changes. Okay, we have that. And then, well, algebraically work out, and y part has characteristic polynomial there, and then we have some other parts, and eventually we get this. Taking partial fraction decomposition is gonna be a pain in the rear end, but it was provided to you. So all right, we get that, and we have the inverse transform. I repeat, from here to there was actually provided to you. So I wouldn't consider this computation as real horrendous computation. It was doable, particularly considering that I gave you those. Anyway, here's our solution. And let me see. Here's a checking process. Turns out, yeah, the left-hand side is equal to e to the negative t power plus e to the t power. Everything works out.